To find the line-to-ground contribution when given the three-phase fault current and the percentage C value, you can estimate it using the formula line-to-ground fault current equals three-phase fault current divided by the square root of 3. The X over R values can be estimated using the percentage C value with the formula X over R equals percentage C divided by 100 minus percentage C. The difference in arc flash categories is likely due to the increased fault current contribution from the utility transformer in the second scenario. The transformer's contribution increases the available fault current, which in turn increases the arc flash energy. It is generally recommended to include the utility transformer in the arc flash analysis, as it can contribute significantly to the available fault current. If you are unable to obtain specific values for the line-to-ground contribution or X over R values, use conservative estimates. This will ensure that the arc flash analysis results in appropriate personal protective equipment requirements. There are software tools available that can assist with arc flash analysis, including the calculation of line-to-ground contribution and X over R values. Firstly, consult with the utility company to obtain as much information as possible about the available fault current. Secondly, review industry standards and guidelines for arc flash analysis to ensure that your approach is compliant. Thirdly, seek professional guidance from an experienced electrical engineer if you encounter difficulties or have any uncertainties. When performing an arc flash analysis using software like SKM Power Tools for Windows, PTW, accurately determining the available fault current from the utility is crucial. Here's a breakdown of how to address the common concerns regarding inputting utility data and interpreting the results. When the utility company provides only the three-phase fault current at the meter and the percentage C impedance, you'll need to derive the line-to-ground fault current and the X over R ratio for both the source. Firstly, calculate the line-to-ground fault current. The utility typically provides the three-phase fault current. To estimate the line-to-ground fault current, divide the three-phase fault current by the square root of 3, which is approximately 1.732. For example, if the three-phase fault current is 10,000 amps, the estimated line-to-ground fault current would be 10,000 amps divided by 1.732, resulting in approximately 5,773.5 amps. Secondly, calculate the X over R ratio. The utility provides the percentage C impedance. To estimate the X over R ratio, you can use the following approximation: X over R equals percentage C divided by 100 minus percentage C. For instance, if the percentage C is 5%, then X over R equals 5 divided by 100 minus 5, which simplifies to 5 divided by 95, resulting in approximately 0.526. Note that this is a simplified estimation. Accurate X over R values require detailed impedance information, which the utility might not readily provide. Request detailed impedance data. The most accurate approach is to request the utility to provide the positive sequence, negative sequence, and zero sequence impedance values, including their respective X and R components. This data is essential for precise fault current calculations, especially for line-to-ground faults. If detailed data is unavailable, use conservative assumptions. In the absence of detailed data, make conservative assumptions to ensure the arc flash analysis is protective. For example, assume a higher X over R ratio, which generally leads to higher calculated arc flash incident energy. One thing to consider is modeling the utility transformer. The inclusion of the utility transformer in your one-line diagram significantly impacts the arc flash results. The initial scenario, where you define the utility at the secondary side and obtain a Category 1 personal protective equipment (PPE) level, differs substantially from the scenario where you include the utility transformer and obtain a Category 4 PPE level. This difference arises because the transformer contributes additional fault current, increasing the overall available fault current at the switchboard. When including the utility transformer, the total impedance between the utility source and the switchboard decreases, leading to a higher fault current. This increased fault current raises the arc flash incident energy, resulting in a higher PP category. It's generally more accurate and safer to include the utility transformer in the model. This approach provides a more realistic representation of the system and accounts for the transformer's contribution to the fault current. Firstly, obtain transformer impedance data. Request the transformer impedance, including the percentage impedance in X/R ratio, from the utility. This data is essential for accurately modeling the transformer in your SKMPTW software. Secondly, model the transformer accurately. Input the transformer parameters, including the impedance, winding connections, and tap settings, into the SKMPTW software. Ensure that the transformer model accurately reflects the actual installation. Thirdly, consider upstream protection. Investigate the protection devices upstream of the transformer, such as fuses or circuit breakers at the utility substation. These devices can limit the fault current and affect the arc flash incident energy at your switchboard. Include these devices in your SKMPTW model to accurately simulate their impact on fault current. In summary, to accurately model the utility contribution for arc flash analysis, perform the following steps. Firstly, obtain detailed data. Request detailed impedance data, including positive, negative, and zero sequence impedances, from the utility. Secondly, estimate when necessary. If detailed data is unavailable, estimate the line to ground fault current and X/R ratio using conservative assumptions. Thirdly, include the transformer. Accurately model the utility transformer, including its impedance and winding connections, in your SKMPTW software. Fourthly, consider upstream protection. Include upstream protection devices in your SKMPTW model to accurately simulate their impact on fault current. Fifthly, consult with experts. If you encounter difficulties or have uncertainties, consult with an experienced electrical engineer specializing in arc flash analysis. Accurate arc flash analysis requires precise input data and careful modeling. By following these steps, you can improve the accuracy of your analysis and ensure appropriate PPE selection for your personnel. Remember that using conservative estimates and including all relevant equipment in your model will lead to a more realistic and safer assessment of arc flash hazards.